Hi everyone, welcome to the fourth lecture on this ninth module where we are discussing the occupancy and motion sensors, and we are discussing the course on microsensors and nanosensors. If you remember, in the previous class we were discussing the optical or optoelectronic motion sensors, and we have discussed that these optoelectronic motion sensors are based on detection of light, mostly in the range of visual or in the range of IR. Okay. So, this light can either be reflected or it can also be emitted from the object itself which we want to detect, right. So, this reflection can happen from the object surface, while it can also emit some light which we can detect and can comment on its position, either it is still or it is moving. Okay. We have seen that there are multiple things that is required in the setup, and the setup was looking something like this. We had a lens, a light sensitive element, and then a window comparator which is connected through this sensitive element through a amplifier, right. So, if the intruder was moving in this field of view of this lens, okay, and it was forming a image at the focal plane, okay, where this light sensitive element is placed, okay. So, the object's image either align with the detector surface or move away from this. Only in that condition we can say that the object has been detected, okay. So, detection can occur only at this two moment when the object's image is aligned with the detector surface, with this surface, or it is moving away. So, we have seen this with one example, that if the detector, if this intruder is moving in this direction, there is no object's image is forming on this light sensitive element, because this is a single pixel kind of camera we have imagined, right. So, we cannot detect if the movement is in this area, okay. So, if the image does not cross the detector, there is no detection, right. This is what we meant with all those discussions, okay. So, we can say that with this discussion that the optical motion detector has a very narrow kind of field of view, right. So, once this object has crossed this area, it will never cross again, okay. So, always you will have this comparator output as 0, okay. So, if the intruder continues to move in say one direction, say for example in this direction or in this direction, their image will intersect with the light sensitive element only once, okay, in the movement in this direction or in this direction, okay. So, it will cross only once. So, you can know his presence if he crosses this light sensitive element field, okay. So, after that the window comparator output will remain always 0, okay. So, that is why we talk that the area which it is covering is very small, okay. So, even you have a very nicely placed sensing area with the lens system and comparator systems, okay, the area that you will be able to cover is very small, okay. So, it is not that it is always a disadvantage to have a narrow field of view. There can be certain cases where a narrow field of view can be acceptable. However, in most of the application, a significantly wider field of view is required, okay, or is preferred, okay. So, to achieve that, there has been several efforts to have a larger field of view, and we will discuss at least two of them, okay. So, the first way with which we can improve the field of view of this sensing element is having multiple detecting elements, okay. So, when I say multiple detecting elements, I do not mean to place multiple light sensitive element, otherwise this will be more complicated, and you may require multiple amplifiers, or you may need external multiplexer to have these devices, and then decision making will be more difficult, okay. So, we have, for such a situation, we have a complex sensing element shapes, okay. So, this sensing element which was looking a rectangular shape over here, or it can be a circular shape depending on what sensitive element you are using, okay. This sensitive element can be in complex shape, okay. One of the complex shape is shown over here, okay. So if the surface, so what I am achieving with this kind of serpentine nature is we are increasing the surface area of this sensing element. Okay. So if the surface area of this detecting element is large enough to span the full angle of view, the area may be optically divided into smaller elements, right. So it creates an equivalent of multiple detector array. So if you see this elements, okay, this elements, not only this vertical elements, but this horizontal elements also, okay, they are acting as a number of detectors, okay, which is placed in kind of array. Okay. So you can think that this is, say, one element, this is the second element, this is the third element, and so on, and they are connected in some fashion to form this kind of array. Okay. So if the surface area of the detecting element is large, okay, so to span the full angle of view, the area can be optically divided into smaller area. I am emphasizing this word optically divided because we are actually, say, if I want to cover this particular surface area, I am not actually dividing these areas practically. What we are doing is we are having separate field of view for all these areas, okay, so that we can have different sensing element with the same sensing, different sensing views from the same sensing element with the help of this kind of array arrangement. Okay. So this is one of the way to have a larger field of view with a equivalent multiple detection array. There can be another way, because this may also increase cost associated with the array of these detectors. Okay. There is one more way with which you can have a larger field of view, which we call it as image distortion. Okay. So instead of designing the detector in a complex shape, what we can do is the image of the entire field of view can be divided into several parts. So you have this field of view, okay, which is divided into a number of, the image itself is divided into several parts. Okay. So this can be achieved by placing a distortion mask. This is the distortion mask. If you see at one place, this blue suggests that this area is blanked. Okay. So nothing can pass through this, and there is this area which is open. Okay. So light can pass through this particular area. Okay. So this can be achieved by placing a distortion mask. Okay. This distortion mask is usually placed in front of this sensing element with a sufficiently large surface area. So what you are doing is, in a place of making this sensing element complex, what you are having is, you are having a single sensing element, of course, with the little wider area. Okay. And then you are placing a physical mask, which is optical mask, okay, which will blank certain areas and will pass certain areas. Okay. So this mask is opaque in this width d, okay, and allow this image formation on the detector surface only within its clearings. So this is clearing 1, this is 2, 3 and 4, right. So these are 4 clearings in this particular mask. Okay. So by this also you can have a larger field of view. Okay. So these are various techniques to improve this optoelectronic based motion sensors. Okay. Now let us see some more example of this visible and near IR motion detectors. Okay. So most of the object except the extremely hot emit the electromagnetic radiations. Okay. Mostly this electromagnetic radiation that is emitted from the object is primarily in the mid and far infrared spectral ranges. Okay. So therefore motion detectors operating in the visible and near IR range have to rely on external light source to illuminate the object, because this object which is emitting this electromagnetic radiation is in the range of mid and far infrared. So you cannot rely on the light which is emanated from the object. What you have to rely on for visible and near IR based motion detectors is to have a separate light source, okay, and this light source can be a simple IR emitter, or it can be a simple LED which is emitting in the visible light, right. So now this light which you are emitting from the source is reflected by the object surface which we want to detect, right, and when it is reflected, it is directed towards the focusing devices for subsequent detection. These focusing devices can be simple a lens based system, okay. So this light source can also be a simple sunlight, okay, it can be a simple electricity bulb or infrared source or infrared LEDs, okay. So essentially if you see this setup that we are trying to see, will have a focusing device which will focus this this light which is getting emitted from a source, okay. Then you will need a reflector to reflect this towards a detector. So essentially you need 4 things, and in the setup you need actually 3 things if you already have a source, okay. You need a focusing devices, you need a reflector, and you need a detector. This focusing devices mostly in this visible and near IR motion detectors are lenses, and mostly it is usually the pinhole lenses, okay. Then for reflections, usually for since we are dealing with visible and near IR, you do not need electromagnetic lenses or electromagnetic deviations for this light. A simple mirror kind of arrangement can act as a reflector, okay, and then you have a photo detector, simply a opto detector, right. So these 3 things are essential to have a visible or near IR motion detector, for construction this is essential, okay. So a pinhole lens which I have just talked about for focusing, actually it theoretically offers you infinite depth of focus, okay. So you have actually infinite depth of focusing range, okay. So what it means is actually you can place your detector nearly to any place which is in its focal plane, okay. So a photo detector can be placed at any distance from this lens, I mean theoretically at least, okay. However, this is limited by various things. So for practical purposes, this distance between the detector and the pinhole lens is governed by the object's displacement, okay, the view angle and dimension of the photoresistor that I am using for the detection, okay. So for detection, usually photoresistors are very popular. So photoresistors, we have seen that for the detectors, that particularly for the complex sensor, that we need to have high surface area, and to have a high surface area, usually these photoresistors are patterned in serpentine nature, okay. So the photoresistors is selected with a serpentine patterned sensing element, and usually this is connected, this photoresistive layer is connected to a low frequency AC amplifiers, okay. The photoresistor is selectively mostly this in serpentine shape, but it can have other shapes also depending on the object movement, okay. So now when the room is illuminated, the motion sensor function like a miniaturized photographic camera, okay. So you have a lens system, a reflector system, and a detector system, okay. So the sensor system works like a photographic camera. Now an image from the lens field of view is formed onto the surface of the photoresistor with something like this kind of arrangement, okay. So you have an object, you have this mirror kind of arrangement, and then you have this pinhole lens, and this forms kind of image that is formed in a camera on this photoresistor, okay. So movement of the people in the room causes this image to change, okay, and that's how it is detected as a change in optical contrast across the serpentine pattern of the photoresistor. So usually this movement of this people appear as a change in the optical contrast, and based on that we can comment on its movement, okay. So because this contrast is changing, of course since this is a photoresistor, its resistance will change, and when its resistance changes, it causes a modulation of the electric current which is passing through the photoresistor, okay. Now this signal has to be amplified, and this has to be compared with the threshold, which is already presetted with the two values. We already have seen there is one positive threshold and there is one negative threshold, and depending on its movement, if the signal exceeds the threshold value, the comparator produce some electrical pulse. Okay, and usually with this visible and near IR motion detectors, along with the comparator we have a timer, okay, which act as a reset. Okay, this reset can be done within say 10 minutes, it can be done within a 15 minute. Okay, so if there is no motion is detected within this time frame of the last movement, the timer deactivate the solid state relay and it turn the lights off. Okay, so the source itself is off to increase its lifespan. Okay, this is how basically visible and near IR motion detector works. Please note that this is completely different with the mid IR and far IR motion sensors. Their principle are very different, and they are more useful in case of military applications or very sensitive kind of application. Okay, so let us discuss about far IR motion detectors also, because they are very crucial for these applications that I have just mentioned. Okay, so this kind of far IR motion detectors work on is based on the optical range of thermal radiation. Okay, so this thermal radiation range is also known as mid IR and far IR range. Okay, now these detectors, the detector of this far IR motion detectors work or it respond to radiative heat exchange between the detector and the object. Okay, so this exchange of heat between the sensing element and the moving object or the object which is of our interest is very crucial for this kind of sensors. Okay, so the principle of thermal motion detection is based on the physical theory of natural emission of electromagnetic radiation from any object. Okay, so we know that any object which is having a temperature which is not at basically at absolute zero temperature, which is having certain temperature, will emit some electromagnetic radiation in the form of heat. Okay, so for motion detection, the object's surface temperature must differ from that of its surrounding object. So if the object is at the same temperature of its surrounding, the thermal cameras or the IR motion detector will be blind in that case. Okay, because it will see that because this is imaging the thermal heat which is produced by the body surface. Okay, so basically it will be blind, it will see it as a surrounding only. Okay, so for this kind of detector, actually to detect, there should be certain kind of thermal contrast. What we are talking is about thermal contrast. So when you have the object which is having a different temperature as compared to the surrounding, actually what you create is a thermal contrast which is similar to the visual contrast in the sensors that we have just discussed. So we had a visual contrast because of which we are able to detect the intruder that we have just seen with the help of all these lens and mirror systems. Okay, so all objects emit thermal radiation from their surface. The intensity of the radiation is governed by the Stephen-Boltzmann law. Okay, so we will see in this course that I am sure that many of you must be aware about this Stephen-Boltzmann law, but since we are discussing a sensor which is actually using this thermal radiation, we have to talk about this Stephen-Boltzmann law in very brief. Okay, so if an object is warmer than its surroundings, its thermal radiation shifts to shorter wavelength. Okay, and because of and along with this shifting of this wavelength, its intensity also increases. So this we will see when we will discuss the Wien's law and other laws. Okay, so if the object is warmer than its surrounding, its thermal radiation shift to a shorter wavelength and the intensity becomes in the higher side, or intensity actually increases. Okay, so what we are discussing mostly is about thermal radiation detection, and basically if you see, this is a heat transfer. Okay, so this thermal radiation is getting transferred from the object whose temperature we are detecting. Okay, it is actually transferring some kind of heat from its surface to the detector. So there are two fundamental properties of heat that we should understand before we actually proceed further in this lecture. Okay, first is heat is entirely non-specific, means once it is generated, it is impossible to determine its source. All right, and the second point is heat cannot be confined. Okay, so these 2 points are very essential regarding heat. Okay, heat is entirely non-specific, means that once the heat is generated, it is impossible to detect what is its source, and second is heat cannot be confined, as it naturally flows from the warmer body to the cooler region of a system. Okay, and no method is known to modern science that can completely prevent this transfer of heat from a warmer object to a colder object. Okay, now once we understand this, we should also understand that how this heat can be transferred. Okay, so the thermal energy can be transferred from one object to another by three phenomena, which is conduction, convection and radiation. Okay, so while conduction and radiation relates to solid, liquid or gases, convection can transfer heat by some intermediate fluid, and this fluid can be both means liquid and as well as gases. Okay, now we also understand that a vibrating particle act as a source of electromagnetic field. Okay, that propagate outward at the speed of light. Okay, now this propagation of electromagnetic field also follow the law of optics. Okay, means that this electromagnetic waves can everything can happen to this electromagnetic wave, similar to the other waves like photons. It can be reflected, it can be filtered, it can be focused, and many more operations can be done on this. Okay, please note that the electromagnetic radiation associated with heat is called the thermal radiation. So thermal radiation is also basically a type of electromagnetic radiation. So wherever we are discussing the thermal radiation, please note that we are also discussing the electromagnetic radiation. Okay, now the total electromagnetic radiation spectrum is very wide. We all know that. You can see this spectrum for your reference. It is shown over here. Okay, so it spreads from a gamma ray to a radio wave, and now this thermal radiation is predominantly situated in this mid IR in this region, mid IR to far IR spectral ranges. Okay, we also know that if this is electromagnetic radiation, this will follow this this law of lambda equal to C by frequency, right? So further, the relationship, although this relationship between wavelength and frequency is not very complex, but the relationship between wavelength and temperature is very complex and is described by Planck's law. Okay, so it establishes radiation flux density. This I am calling is W with a subscript lambda. I will use the word W. Okay, as a function of wavelength. I am using this subscript because it is a function of wavelength. Okay, so this Planck's law establishes the radiation flux density W as a function of wavelength and absolute temperature T. Okay, so the radiant flux density is the power of electromagnetic radiation per unit wavelength. Okay, so we have to come up with the equation of this radiant flux density, and Planck's laws of black body radiation gives this equation for this radiant flux density, which suggests that this radiant flux density is equal to this emissivity, which is the object's property, into C1 by pi into lambda to the power 5 into e power C2, which is again a constant similar to C1 by lambda t minus 1. This equation is very crucial, and this is a form of Planck's law of black body radiation. Okay. Now, this C1 and C2 are constant, as you can see, and this is the emissivity of the object. Okay. So, this equation defines the radiant power at a specific wavelength lambda as the function of object's temperature T. Okay. Now, temperature we know that is determined by the average kinetic energy of a vast number of vibrating particles. Okay. However, please note that all particles do not vibrate with the same frequency of the magnitude. Okay. So, because of this there is a wide range of frequencies that is possible. Okay. So, since they are vibrating at different temperature, actually different permeable frequencies are spaced extremely close together, allowing the material to emit an almost infinite range of frequencies, and this extend from very long wavelengths to very short wavelengths. Okay. Now, since temperature is a statistical measure of average kinetic energy, it indicates the most probable frequency at which particle will vibrate. Okay. And that is what we deal with temperature. Okay. And the corresponding wavelength they are likely to exhibit. Okay. So, this gives both temperature and wavelength. Okay. So, the most probable wavelength is established by Wien's law. Okay. This can be found by equating the first derivative of this equation to 0. Okay. And when you equate it to 0, it says that the wavelength is given as 2898 divided by T, where this T is in Kelvin. Okay. And this lambda max is the wavelength in micrometer. So, the result of the calculation is a wavelength near which most of the radiant power is concentrated. So, all this radiant power is concentrated along lambda. Okay. This Wien's law states that the higher the temperature, the shorter the wavelength, and that is what we have seen from this curve. Okay. So, when the temperature is increasing, this is shifting towards lower wavelength and the intensity is rising. Okay. And this curve is given by Wien's displacement law. Alright. Fine. So, what we are going to do is we are going to use this in our far IR detectors, which is very crucial for military applications. Okay. So, Wien's law also states that most probable frequency in the entire spectrum is proportional to the absolute temperature. Okay. And this frequency is given as 10 to the power 11 into T, and this value is in hertz. Okay. So, at normal room temperature, most of the mid and far infrared energy is radiated from the object is in certain terahertz, mostly 30 to 31 terahertz. Okay. So, according to Planck's equation, this equation that we have seen, the frequencies and wavelength of radiated energy depend solely on the temperature, because if you remember, we have seen this equation for the radiant power for particular wavelength at particular temperature. So, it says that it solely depends on temperature. So, the radiant flux density for the three different temperature for infinitely wide bandwidth is shown over here. Just let us understand this with one example. This is for 0 degree Celsius, this is for 100 degree Celsius, and this is for 200 degrees Celsius. Okay. It is seen that the radiant energy is distributed over a spectral range of which is highly non-uniform. Okay. So, this clearly pronounced there is some certain maxima which is defined by the Wien's law. Okay. So, this is a non-uniform distribution and the maxima was defined by the Wien's law, and that is how temperature is also defined. So, it is a average of the kinetic energy, and it suggests the maximum particle is at what particular temperature. Okay. So, the intensity of the radiation is also influenced by the emissivity of the surface, not only by the temperature. Okay. So, this emissivity thing which also govern the intensity we have to see, because it is a key characteristic of a thermal radiation sensor, because we will use this emissivity property to design our sensor. We are discussing all this heat transfer and other things just to design our far IR and mid IR sensor, which is based on the emission. Okay. So the conclusion is the intensity is not only defined by the temperature as suggested by the Planck's law, but it also depends on the emissivity that we will discuss maybe in the next lecture. Okay. So in the next lecture we will mostly cover this mid IR and far IR motion detectors. Thank you.